Yes. It's okay? Can you see the screen?
Yeah. Yes, perfect.
Great. So I'm going to talk about our paper in this special issue on massive connectivity and critical services. And these are my co-authors from both academia and industry that contributed to the paper. So this this quest for going to massive connectivity and for going to massive connectivity and to critical services started in 5G. And because we talked that besides the broadband connection, we have to introduce two other classes of services. One was massive access, mostly focused on low energy, and the other is ultra reliable low latency communication, which coupled latency and reliability. So these are two service classes for IoT introduced in 5G. And then the question is how they're going to evolve in 6G. So the support for these small devices, for example, in the case of URLLC, they're not small. That could be robotics applications, bionic limbs, and so on. So the support for the evolution within 6G is driven first and foremost by the ubiquitous intelligence, because the question is, will this device only provide real-time data to various AI modules, or some of them are going to embed certain AI modules to process the data and make decision, or for example, implement certain form of inference. Then another is the security, privacy, and resilience. The third driver is to connect the unconnected. For example, now there is a satellite connectivity based on NB-IoT, which is already operational, and which can offer transmission of messages in unconnected areas. And probably this is going to, not probably, but almost certainly evolve to support of voice and so on. And also the sustainability, in a sense that whether this type of devices could be used to monitor other processes, for example, for Earth observation, for smart energy, and so on, which is kind of a legacy from, I would say, already from 4G and 5G. But we do not stay with only these two classes as defined in 5G, and there is evolution there. And 6G augments each of these services classes within the class, but also across the two classes. So first, within the class, massive machine type communication, and this is also discussed in the paper in details, is augmented by going to non-terrestrial networks. So basically supporting large number of devices in large areas covered by satellite. And another important is the closed loop. So because within the 5G, massive connectivity was mostly understood as an uplink, transmission from the sensors to the infrastructure. However, there are multiple reasons to have closed loop connection. For example, the closed loop could be, the downlink could be used to update the devices, also could be used for real-time control, but it could also be used to flexibly allocate the resources uplink, downlink, depending on what the ubiquitous intelligence requires, so where the AI modules are put. On the URLLC side, instead of insisting on strict latency, we actually go to generalized timing requirements. And I think we have a better understanding of what real time means. I think Josep mentioned this within his talk, that processing large bandwidth, it takes considerable time and resources. And actually, the radio part of the latency might be even the smallest. Compressing, computing, inferencing, all this takes time. So we try to understand what is the generalized timing measure. And in this way, we are augmenting URLLC. And finally, not only reliability, but we are now there is a lot of discussion about robustness and resilience, and I'm going to make differentiation between these notions. And also there are types of critical services with massive IoT. And this is interesting, because if you can offer critical services with massive IoT, that means that each of the IoT devices contributing to the massive connectivity should be extremely reliable. Actually, that's not correct, because this is the case where the content of the massive devices is correlated. So we have multiple sensors that are detecting the same event. The question is, how can they all report the event without conflicting with each other, but in some way coherently delivering the message about the event. So, from this, it becomes clear that massive connectivity will evolve beyond sporadic uplink, as it was foreseen in 5G. And there is a mix of uplink and downlink traffic, and this is requested by increased presence of AI. You know, we are not in a situation to predict how AI is going to affect the traffic, but we say we better have two-way connectivity, so to serve the needs of the inference or learning of various AI modules that will be placed either in the network, edge, or the devices. Then closed loop performance for sense, compute, actuate cycles. This is a bit related to what Yasemin was talking before, robotics and connected devices, where and also what Nuria was talking about, sensing, because one thing is to gather the data from sensing, and the other is to go into robotics and then do this in real time, computing, inferencing, and then actuate, like in the drones or UAVs to make maneuvering in real time. Then another thing that is driving this is digital twins. So the digital twins of a physical environment, which are supported by updates from multiple sensors. So we actually want to instruct which sensors to transmit. There's a downlink transmission, but we also want to collect data from them. There's uplink transmission. And another thing is the data storage and verification, you know, the authenticity and the trustworthiness of the data. And we expect that there will be a wider spectrum of devices going from zero energy devices, which can very sporadically transmit, to AI-powered IoT that can autonomously gather data and make decisions. On critical services, I think as I said, we are going to generalize the timing requirements. So, which is required by network control and connected robotics. So instead of just looking into latency, we look into the full timing of the closed loop, and measures like age of information or value of information, which contribute to a certain type of action or a certain type of actuation that is done within these systems. Previously, we talked about service guarantees in 5G. And by time we understood much better what it means to give, for example, reliability of 5 nines or 7 nines. And we need to use statistical methods to verify this. Another line of work is to make digital twins of wireless environments, by which we're using the digital twins to predict what will be the performance in terms of high reliability. And this is related to sensing of the environment, calibrating the models, and so on. And unavoidably, we're using AI-based techniques to kind of, for example, generate the channels that appear in the environment, and then based on these generated channels, try to predict what will be the performance. Last thing I want to mention is that we have to make a differentiation between reliability, robustness, and resilience. So reliability was very much focus of 5G, and it is about known impairments, for example, channel fading, with known statistics. Robustness is about known impairments like blockages, but with unknown statistics. So we do not know what is their statistics, but we have to react when they occur. And this is done by hardening the system in terms of better control information, more spatial diversity, and so on. But resilience is different from all of this, because in resilience, we have unknown impairments and we have unknown statistics. So we don't know what can hit the system. So resilience means that after the system breaks down, the performance breaks down, it is capable to go to a fallback solution and then come back to the maybe a bit reduced functionality. And this requires both engineering and, let's say, some AI techniques. So with this, I would finish my presentation. Thank you.